אם את מבינה, כאילו, בסדר, היית כבר את זה, זה לא שעכשיו, זה לא גמרות, כאילו.
אני מרגישה, כשאני ארגיש יותר בפנים, אני אצליח להוכיח שזה כאילו
לא בטוח שדרך אחרת טוב. אולי.
אתה לא חושב שיש דרך אחרת?
לא, אני בטוח שיש דרך אחרת. מאופיין של טענות נכונות שאפשר להוכיח אותן בכל מיני דרכים. אבל השאלה היא מה כל דרך מלמדת אותה.
בסדר, פה זה בעיקר בשביל הביטחון העצמי שלי.
טוב, לזה קשה לי לעשות.
כן,
לזה קשה לי לעשות.
זה הסיבה שבחר כאילו.
אבל אני חושב...
רק לפרגן למלא. מורה הכי יפה, הכי טובה.
כי אני חושב שלהציג את ה-Unitary Transformation כ-DKL בין הג'וינט לקראת המרג'ינל.
מה? יונתן, למה זה מה
זה גם איך שהוא אומר לך למה Unitary Transformation זה מדד לינק.
מה?
אני מוקלט, יכולה לשמוע את זה אחר כך. כל החלק הזה שלה, אבל אנחנו עושים היום. אני כבר לא תורה לעשות. זה כל כך טוב. היום יש לי שאלה. יש לך שאלה. שאלה אחר כך? או שאתה רק כאילו, אני חושבת שבאחד דבר אפילו אפשר
באלף?
אם יכוון כבר, אוקיי.
אבל גם זה כאילו מקרב אחר הרבה, כאילו תראה, אני לא עובד עליהם, זה הרבה יותר ממה שנתתי תוך כדי.
יש 5 דקות ראשונות, 5 דקות מבוכה. אני חופרת, אני שרה. כנראה זה גם יקרה עכשיו, כן?
או כל פעם שאני רוצה, אני כאילו משתמש בהם ולא משתמשים עליהם. גם בזה שלא תעלה. שמעתי בסיפורים שלי. אני רוצה לסכם את השיעור.
וואי, גיא.
כן, לפני זה.
כן, גיא.
למה? כי זה דברים שאני כתבתי, אז אני כאילו, אתה יודע, יש לי כאן את המדיאל של מים, מיליארית סייל, אני רואה משהו שזה הצעה.
זה מעניין, איזה לכתוב.
אני לא נורא משקיע, כן? לא כמוה.
אתה מנסה לגבות לי עכשיו?
אני רוצה להסכים את האמיל ליאור.
ממש. עם כל הסיגנל טו נויז רשיו הגרוע שלי, עם כל הקשקושים.
כמעט לא קרה
שלמדתי סיכום עם סיכומים שנכתבו באותה שנה.
מה?
תמיד יש סיכומים משנים קודמות.
זה הגוף שלהם.
יש, בדרוגות. אני חושב...
יש משהו שיואב ואלה.
של יורון.
אבל נראה לי מינימליים כאלה. כאילו, משוואות.
מה?
מינימליים.
הם די מינימליסטים, אבל הם ממש מקבילים למה שהוא כותב על לוח, אז אני חושבת שזה ממש הסיכום שלו.
איך מדעת
זה
שהוא
של יואב.
אוקיי.
מה אתה הולך היום? אני יודעת מספר שיעור.
את יודעת את מספר שיעור, אבל לא את התאגיד.
זה בדיוק היופי בredundancy, שאני יכולה...
בסדר, יש גבול לכמה אני צריכה לפתוח את הפתיחה.
דווקא נראה שאתה נהנה. הבאתי משהו היום. לא התחלתי את זה.
Okay, so far we discussed efficient coding of a large number of inputs by one output unit. And within the assumptions that we took, the conclusion was that the best way to do this is to project, when we linearly project the inputs into one output unit, the best way is to choose the direction which corresponds to the first principal component of the statistics of the input. Why? Because that's the direction in which the projection will have the largest signal to noise ratio. So now what we want to do is to generalize what we've done to the situation where we have not only multiple inputs but also multiple outputs, which is much more relevant for a sensory system. The sensory systems typically do not encode the multidimensional input by one neuron, they encode it by many. So let me first remind you about the formulation of the problem. We've already written it, but I'll just write it briefly again. So we have our units and the input units, the output units. Each output unit in general can receive inputs from all the input units. So this was n units, this was m. And we denoted the receptive fields by by a matrix Wij, which was n by m. And the inputs we denoted by a vector x, which is n-dimensional, plus input noise. And the outputs were W transpose, the matrix W transpose, multiplying x plus Z in, right, plus Z out. Z out is the output noise. And then Z in and Z out are uncorrelated Gaussian and with variances this is Gaussian. And this you can see?
I can see that.
Okay, last time I think this was still, it depends where you sit. So so Z in, Z out are uncorrelated, Gaussian, and the variances we denoted by Xi for the input noise, I think, and delta for the output noise. Epsilon? Epsilon here, yes. Epsilon and delta. So these are the noise variances. Okay, so the signal, which is the input, undergoes several things. It's corrupted by noise at the input. It's then projected through this matrix W, and then the output is corrupted by noise again. Okay, and our goal is to maximize the mutual information between the outputs, which is Y, and X, mutual information with a constraint. Our constraint was on the variance of the activity of the output units, namely that sum over I going from 1 to n yi square is equal to m times q. So it's just a way that we decide to parameterize it, that q is the variance per output channel. And so before we delve into this problem mathematically in detail, it's interesting to discuss what we can expect. So I will start to write it here. No, that's not good. Okay. So the first thing that we need to discuss is what is the subspace? What is the m-dimensional subspace that will be optimal? And what do you think? Just based on what we've already done. First, m principal components. Okay, so in the one-dimensional case, we concluded that the best thing was to project on the first principal component. Now we have an n-dimensional space. We can add many more output. We increased by a lot the dimensionality of the output subspace, and the same reasoning applies. The projection on the m-dimensional, on this particular m-dimensional subspace, that's a subspace in which the input x has the largest variance, and therefore that's the subspace in which we will have the least corruption by noise at the inputs, by the input noise. So the choice of subspace, first m principal axis. Now, before we continue, now I want to go into a slightly technical point, which many of you know, but I think it's worthwhile to write it. I think all of you know this, but it's worthwhile to write it. And this is just, I want to ask, technically, what do we need to do in order to extract the first m principal component? What does it mean? How can we write it mathematically? Or what does it mean to project on the first m principal component? So I do this on the side, and then we'll continue. So yeah, what is it? How do we write it mathematically? Projection. Coefficients of projections on first m principal components. So what does that mean? So first, let's just remind ourselves what are the first m principal components. So we have a covariance matrix of the inputs. Let's write the covariance matrix. So let's imagine that that's Cij. So that matrix has some a set of eigenvectors, a set of n eigenvectors, and with corresponding n eigenvalues. Let's denote them by ui, the vectors ui. So these are the principal axes, the eigenvectors of the covariance matrix, and I goes from 1 to n, right? So these are the directions in which we want to project. And note that if we look at the covariance of inputs with noise, it's Cij plus epsilon delta ij. right? Because the noise is isotropic. It has has the same variance in each component and independent. So this is the covariance matrix of the noise. What are the eigenvectors of this matrix? The same, right? A matrix which is proportional to the unity matrix, every vector is an eigenvector of that matrix with eigenvalue epsilon. So it's immediate to see that every one of these vectors, when you multiply it from the right by this matrix, we simply get the same vector with a factor lambda I plus epsilon. So it's the same eigenvectors, and the eigenvalues are the same eigenvalues as in this matrix plus epsilon. Okay, now these vectors ui are orthogonal, and we can be chosen to be normalized. Let's choose them to be normalized. So technically speaking, I remind you, it's easy to show that two eigenvectors that have different eigenvalues must be orthogonal to each other. And if there is more than one eigenvector with the same eigenvalue, we can choose them to be orthogonal to each other. So we can choose the UIs to be orthogonal and normalized, and that means that U transpose K. Now let me just do one thing. I want to put the indices here, just to remind ourselves that these are not the indices of the vector. These are this index I is just telling us which one of the eigenvectors it is. It's not the index corresponding to the different neurons. So I just prefer to write it this way. So now this means that U transpose K U L is delta KL. So now I come back to the question, what does it mean to extract the coefficients of the M principal components? So what does it mean to extract? If we have an input which is xi plus z in I, that's a vector of inputs. We know that we can always write it as a combination, linear combination of all the principal axes. That's because they form a basis. So we know that we can write it down as some sum over all the k's going from 1 to n, ck, u, a, I, k. And what we really want to do is to extract these c's. All right? That's what I mean by extracting. We want to know what are the ck's. So how do we find the ck's? You know this? How do we find these coefficients? We multiply by the left by these vectors, and we make use of the fact that they're orthogonal and normalized, and that will just pick up when we multiply by one of these u's from the left. For all, if they say we choose UL, then for all k different from L, we get 0 because UL, UK is 0, and for k equals to L, we'll get CL. So I'll write it down. So C, let me use instead of L, I will use J. Cj is equal to U transpose J times the vector X plus C in, which is like doing the sum over all indexes I going from 1 to n, U, I, J, X, I plus Z in I. Okay, so the reason I did all this is to see that if our goal was just to extract all the coefficients of the principal components, all n of them, then we can describe the operation that we need to do as multiplying our input vector with the noise by a matrix. The elements of this matrix is the ith jth element or the jth ith element of this matrix is the ith component of the jth eigenvector. Okay, and we will use that in a bit. Okay, so but going back to going back to what I was saying here, if the subspace that is being the best subspace to choose is the first m principal components, then this would be like doing this linear transformation that I described here, but just taking the first m. But then we're still free within that subspace to decide how to, what in principle we can take any combination of them. So that's what we want to discuss next.
What do you mean, any combination? We just said that we need this.
Yeah, but we said that's the subspace. The subspace is the first m principal components. Let's suppose that we do a two-dimensional representation. So we have the first two principal components. We know that that's the subspace we want to project to. But the question is now, do we just encode each one of them, the C1 and C2, do we encode them independently of each other, or do we encode some combination of them? Okay? We can encode maybe C1 plus C2 and then C1 minus C2. Principle. That's by saying that I'm only taking the subspace, all I'm saying is that I'm eliminating any information about the Cm plus 1 to Cn. I encode only C1 plus to Cn, but I can do this, still I have the freedom to choose any linear combination of these. Okay, yes?
Can you repeat the last point that you made over there?
I don't know what is the last point.
I couldn't see, and you said a lot of indices names, and I lost.
I just said that extracting the coefficient, so if the set of inputs, we think about it as a linear combination of all the principal vectors, you want to extract the coefficients, this is what we need to do. If we want to extract the coefficient Cj, we need to multiply this vector from the left by the vector uj. Okay, and this is really a linear, so the transformation from all these inputs to all the C's is just a linear transformation. And we know what it is.
What is by every principal component by coefficient? So what do you mean combination of coefficients?
So if I would, what I'm saying is now if I choose C1, just this is, there are n of these guys, right? Now I'm saying we're projecting actually to an m-dimensional space, and I argue that the best thing to do, I didn't prove it, but I argued that similar reasoning as what we did for one-dimensional output is we need to choose just C1 to Cm. But now I'm saying in principle maybe we should encode not separately C1 to Cm, but we could encode take this m-dimensional vector and do some linear transformation on it and encode that. This will also be an m-dimensional vector. Okay? But this will become clear, I think, more clear later. Because actually what I'm going to argue right now is that under our assumptions, where the inputs are Gaussian, we know that these numbers, C1 to Cn, or also C1 to Cm, are uncorrelated. Because when we switch to this basis, we did a linear transformation. We switched from the basis of these guys, I going from 1 to n. Let's still be in the n-dimensional space. We switch to C1 to Cn. If you're not convinced, the C1 and Cn, the correlation matrix of them is diagonal. Okay? Now, they're also Gaussian. They're mutually Gaussian because this is a linear transformation over Gaussian variables. So we know that any multidimensional Gaussian, you do it on a linear transformation, you still get a multidimensional Gaussian. So these C's are not only uncorrelated, they are also independent because for Gaussian variables, that's the way it works. If it's two components of a multidimensional Gaussian variable are uncorrelated, they're also independent. So these CJs, maybe I'll write it down, are uncorrelated. Oh, no, I'll write it down here. So the CJs are uncorrelated and independent. If they're independent, it actually does make sense to encode them separately, because if they're independent, there's no redundancy. If I encode C1 and then I tell you something about, tell you what is C1, it provides you no information about what is C2 and what is C3. So it actually makes sense to encode them independently of each other. And so that's a possibility, that one way to do this that we will explore. So
Sorry, I still don't understand what does it mean to encode the thing.
it means that the output units, it means that each one of the output units, that we will choose this matrix W such that it will extract, for the first output unit it will extract C1, for the second output unit it will extract C2, for the third output unit it will extract C3, okay? So that means that each output unit will correspond to one of these coefficients. We could have done something else. We could have now combined them linearly, and we're not going to do it because of this argument that the C's are actually independent variables, so it makes sense to encode them independently of each other.
You're saying that when you move to the eigenbasis, you remove all the, you are left only with the independent.
Yes.
And are there indications that this is what is done in your system?
Oh yes, we will discuss that. Hopefully we'll manage to finish this week or next week and discuss the retina, and I will argue that that's exactly what the retina is doing. Okay. Now, but there are some complications that we will need to understand. But there is one issue which is subtle. We'll get back to it also later. For Gaussian inputs, uncorrelated and independent is the same, right? Now, for whether the inputs are Gaussian or not, that's a question about the natural inputs that we encounter. So if we think about the retina, our visual inputs, the activation of the photoreceptors, are they Gaussian? The answer is no. So we'll have to discuss that later. But for now, we assume that it's Gaussian. All right. So given this observation, what seems like the simplest choice to do an efficient encoding of the inputs with an m-dimensional space is to encode each of the first principal components separately. Now, going back to what you asked, what do I mean by that? Now I will write it explicitly. What I mean by that, I don't know if I should continue here. It seems like, so I continue here. What I mean by that is now that I want to choose W transpose such that it will extract C1, C2, C3. But I know, given what I've written here, I know exactly what I should do. Wij, what should it be like? What should it be? It should be Uij, right? Because, see here, the matrix, this is really this you can think about Uij as matrix W transpose that works on this vector. So if I choose Wij as Uij, where now J goes just from 1 to M, then if I apply this matrix on the vector of inputs x plus z in, I will get exactly what I called the CJs. Now, at this point, it's not clear that that's exactly what we want to do. I just want to project on the inputs, but I still have the freedom to encode each one of them with a certain amplitude. I can multiply, you know, the jth component. I can multiply it by some factor, which we still need to determine what will be the best. Okay, so I will denote this factor by square root of alpha j. Okay, why square root? For the same reason that I used square root when we did the one-dimensional case. It's just we'll need to deal with the square of this thing. Now, in the one-dimensional case, alpha j was trivially determined by the constraint which is written here, right? It was very easy to, once we decided what is the projection, first principal component, the coefficient was just set so that the variance of the output will be what we need. Now it's more subtle, it's more interesting. It's more interesting. We have an m-dimensional output, so we have a freedom to, it's not just a question of, you know, it's not that our constraint is not on the variance of each output unit alone. Our constraint is on the sum of the variances. So there is a question of how much resources are we putting into each one of the output units. We can increase some of the alphas at the expense of others and still maintain this constraint. So the question is how much. The larger alpha for a particular component, it means that we're allocating more resources to encode that one. So the question is, how do we decide on the balance between the different outputs? And that's something that we will need to understand. And in fact, there are some very interesting things that happen, which I will discuss next. Do we want to make the alphas larger for the components with the larger variance? The first principal component, do we want to make the alpha of the first principal component the largest, or we don't want to make it maybe smaller than for other principal components? So we will see in a moment that the answer to this question is not trivial. It depends on conditions. And that's what we want to discuss. I want to discuss next. So what I want to do now is discuss how these alphas, how will they behave in two limits. One is the limit where there is lots of input noise, and one is the limit where there is very little input noise. So I'll start actually with the second situation, low input noise. So let's imagine, again, there is very low input noise. Right, so you can see here why input and output are different. The input noise gets multiplied by W, whereas the output noise does not. Okay, and we will see in a moment why that matters. So low input noise means that I can say that Y, the outputs, are to a very good approximation, simply W transpose X plus Z out. Okay, so note, at this point, I completely ignore the input noise from here on, and we'll see what that means. But before we continue, I just want to comment that we didn't ignore the input noise completely. We did use the existence of the input noise in one very crucial way. Can you tell me what it is? I'm telling that even if the input noise is very, very low, it plays an important role in what we're doing. Exactly. The input noise is the reason why we're choosing the first M principal components. Because remember, that's the question of when we do this projection, before we even add the output noise, what is the direction in which we'll get the largest signal-to-noise ratio? This is due to the input noise, right? If the inputs, have some statistics like this, suppose it's two-dimensional, and the input noise is isotropic, well, I would want three-dimensional. But in two dimensions, we want to project in this direction, because in this direction we have the largest ratio of signal of X compared to the input noise, and that carries through to the higher dimensions. So the input noise still played a role here in the fact that we chose the first M principal components, but from here on we ignore it in this limit. Okay, so now in that case, if that's the structure of Y, then the mutual information between Y and X is, it's the entropy of Y minus the entropy of Y given X, and that's the entropy of Y minus the entropy. Now, the entropy of Y given X, now if there's no input noise, or if the input noise can be neglected, then this is just the entropy of a constant plus the noise, and so it's just like the entropy of the out. And this is completely independent of our choice of W. Right? This is independent of W. So that means that in this limit, where the main source of noise is the output noise, maximizing the mutual information between y and x is just like maximizing the differential entropy of y. Okay, so our goal in this limit, so maximizing I of y and x is like maximizing h of y. Okay, but so now y is a multidimensional Gaussian variable, and it has this constraint on the sum of variances of its inputs. So should we get when we maximize its entropy? So if you have an m-dimensional Gaussian variable, with this constraint, what is the form of that variable that maximizes the entropy? It's what? No lambda, no need for a lambda. Symmetric, uncorrelated, so it's isotropic. So isotropic. The form of a Gaussian variable with a constraint like this, that that maximizes the entropy, is when all the elements are completely independent, are uncorrelated, and with the same variance. So without any work, we know what the statistics of y should look like. So y should be spherically symmetric Gaussian. And that means, I will continue here, that the average of yj, yk must be delta jk times what? If it's isotropic or spherically symmetric, it means that it's the same regardless of the index. And what is the value? That I should q, because that's just because of this constraint. So that's what yjk should be. But we can also write yjk, just a second. On the other hand, it's also equal to, I mean, with this scheme where the y's are these principal components, then the variance of then I claim that indeed, if we use this scheme, different y's with different indices will be uncorrelated. Okay, you can check it if you're not sure. And the variance of each y will be what? It will be the variance of this thing. And remember, we're neglecting the input noise. So this will just give us the variance of Cj, which is 1, multiplied by the square of alpha j. So that would be the variance of the variance of Cj is equal to lambda j. Okay, so I will write it, and then I will explain a bit, but I will not go through the steps. Will be your job to go through the steps and convince yourself that that's true. The variance of yj is going to be the variance of the projection on the j's principal component, which is lambda j. But we're multiplying it by square root of alpha j, so that gives us another factor of alpha j. And then there will still be an added variance coming from the output noise, and that variance is simply delta. So this is when j is equal to k. So what do we get out of all this? What we get out of all this is what are the alpha j's, because we now compare this and this, and we conclude that alpha j should be, the best choice for the alpha j's should be q minus delta divided by lambda j. Okay? So what does that mean? It means that I'm not sure. I think I'm using things that I've discussed, but maybe I think you will need to check it for yourself and see that it's correct. Okay. The crucial part, which I did not write explicitly, is that what is the variance of each one of the CJs? And I claim that that is lambda j. Lambda j, actually, the eigenvalues of the plus the input noise, but we ignored the input noise. So the eigenvalues of the covariance matrix encodes what is the variance in each one of the principal directions. Okay, so the first principal direction has a variance lambda 1, the second principal direction has a variance lambda 2, and so on. Now, this is interesting because it tells us something about what the system is doing. What it tells you is that in this limit of low input noise, we devote the most resources to the first principal component. The higher the lambda, the smaller the lambda. Sorry, no, the opposite. No, the smaller the lambda, the larger alpha. Okay? Smaller lambda, larger alpha. So we're actually suppressing the directions in which there's the most variance. It's like we're equalizing the variance of all the. So we have some input. We have some input which has, more variance in this direction. Let's suppose that this is already after the. I'm writing in an area that you don't see. Let's suppose that this is already after the projection to two-dimensional space. We have a direction in which there is more variance and a direction in which there is less variance. So we're actually equalizing it. We're the directions in which there is less variance, we're multiplying by larger factors such that we'll get the same variance in all directions. So we're devoting more resources. We're suppressing. Let me see how I wrote it in my notes. We're suppressing the directions with a larger lambda. The reason we do this is that the reason we can afford to do this is that there's no input noise. So if there's no input noise, we don't lose anything by expanding some directions which have less variance. But if there was input noise, we would lose something out of it by doing this, by expanding the directions in which there's little variance, because these directions has a larger signal-to-noise ratio, a smaller signal-to-noise ratio than directions with large variance. So this is what we're actually we're enhancing the directions in which there's smaller variance. Yes?
I don't understand what you get more from these situations than just assuming that there's no noise at all and then get that each direction is the same. Because it seems like
you're right. The output, the role here. Well, it's actually this is actually what we've done. We assume that there's no input noise.
Yeah, but you said that you still use so it will be important to choose one of the direction over the others, first principal components.
Right. So if there was really no input noise, we could have chosen just as much any one of the principal components, not just the first M. So there's because if we take the limit where the input noise becomes smaller and smaller, what happens is that there is still a slight advantage in choosing the first M compared to the other ones.
How do you see it?
I'm claiming it. I'm not proving it. Okay, but I didn't. This is just this. This is statement number 1, which I didn't prove. I just argued it's correct.
Yeah, but
Okay.
my point is that what you get at the end of this.
So in the strict limit where the input noise becomes completely zero, it doesn't matter in which directions you project at all. You can project in any directions that you want, orthogonal set of orthogonal directions, but as long as there is even a little bit of input noise, then that breaks the symmetry between all these directions. The directions with the larger variance are better in the sense that they have higher signal-to-noise ratio, but then what we do with them later on is dominated by the output noise and not by the input noise. Okay, and that's what we got, and that's what we want to do. And I argue now.
But at the end you equalize them, right? So it seems like you get to the same.
So again, so strictly speaking, if there is little bit of input noise, you will not do this exactly. This is just in the limit where the input noise goes really to zero. So you will never do this exactly, but in the limit, that's what you do. So in that limit where the input noise becomes small, you project on the first M principal component. That's the only place where the input noise matters, and then you do this. Okay? Let's discuss now what happens if there is large input noise.
So does really equalize them or just making them?
You almost equalize them. If there's a little bit of input noise, we'll write down mathematically what you need to do for general case. Okay? But then we'll check back that we're actually getting these results. So
it needs to be like large enough so it will break the symmetry, but small
yeah,
enough so
in some
like
sense,
how
yeah. That's what the math. That's what the math is telling us. Okay, let's believe the math, and then ask whether it's relevant to something in the brain. I'll claim that it is. That's exactly what the retina is doing. Okay, let's discuss. I just want to discuss large input noise, and then we'll take a break, and then we will go through the whole thing again, doing with more mathematical details, treating the general case. So I claim that if there is lots of input noise, doing this is a very bad thing to do. Because actually what we're doing is we're taking, so imagine again that that's our variance of the projected inputs into the first two principal components. And now on top of that we have a huge input noise. Then in that case, this direction, projecting on this direction carries much more information about the signal than projecting on this direction. And yet what we're doing here is we're actually suppressing, we're devoting more resources to encode this direction than to encode this direction. So it doesn't make sense. In the case where there's lots of input noise, it actually makes sense to do the opposite. So I'll just write it down as a hypothesis that that's what we should do, but we will see that that's what the theory will tell us later on. So in case of large input noise, what we expect, okay, I remind you I have this title expect here. This is what we expect. For small lambda, there's a small signal to noise ratio, or another way to express this is a little information about X after corrupting by the input noise. So we would want to suppress the projections on the directions with small lambda and large lambda, lots of information, enhance. So we will see later when we treat mathematically the problem more in detail. We'll see that that's actually what the theory will tell us. And so what the theory will tell us is that these alphas, the alpha that appear here, have very different behavior when there's lots of input noise versus when there's very little input noise. In both cases they're monotonic, but in different directions. When there's very little input noise, these alpha j's increase with j. Okay, we're enhancing the directions with little variance, and when there's lots of input noise, these alpha j's will decrease with j. We will suppress the directions with input noise. And so before we continue with the math, I just want, because I brought up the retina several times, I want to just tell you already that these predictions relate to something that we can check about our visual system. Because changing the amount of input noise to the retina is something that we can do very easily. The input noise in the retina, at least in some range of intensities of light, arises from a source which is external to the retina. It's just the statistics of photons hitting photoreceptors. Okay, so the number of photons that hits the events of photoreceptors, photons hitting photoreceptors are just Poisson events, and that's from physics. That's quantum mechanics. There's no way around it. And so, the lower the light intensity, it's in a sense the system is more noisy. It's events which are, it's just like we discussed many times. When you have something which is at a high rate, then the noise relative to the mean becomes smaller. When something happens, the Poisson process has a low rate, and the noise, the variability relative to the mean becomes larger. So for the retina, going to low light intensities is like going to low input noise. We'll discuss this in more detail a bit later. And so all this has clear predictions on perception. It means that in low intensity, we will be more sensitive to some components of the input. We need to discuss what they are. What are the principal components of the visual signal? We'll discuss that later. But in low input noise, we'll be more sensitive to some components of the visual signal. And at high light intensity, which is like low input noise, we'll be more sensitive to other components of the visual signal. And in fact, that's exactly what happens. Okay? We'll discuss that. Not only is that true, also the structure of receptive fields is predicted by the theory, but to understand that, we need to go through more elements. Okay, so let's take a break. כי בפועל אנחנו אף פעם לא במצב שאין בכלל רעש באינפוט. אז נגיד שהמערכת הוויזואלית צריכה להחליט איך לעשות את ה-dimensionality reduction מפוטו-רספטורים ל-dimension, צריכה לעשות איזושהי בחירה. הטענה היא שהבחירה שהיא עושה היא בחירה שבאמת מבוססת על הכיוונים שבהם בכל זאת יש יותר וריאביליות.
אבל בסופו של דבר אתה מגיע לאותה נקודת תחנה, שזה לא משנה.
לא, כי הפרוג'קשן הוא עדיין הכיוונים הבחירה של הסאבספייס, של ה-n-dimensional space, היא מהסטארט. זה לא נכון שזה לא משנה, זה משנה קצת. כל עוד יש מעט input noise, זה משנה, זה נכון שזה משנה קצת, אבל עדיין זה משנה. אז עדיין שהבחירה של הסאבספייס עדיין נשלטת על ידי ה-input noise. ובתוך הסאבספייס איך זה מקודד, זה כבר נקבע על ידי
כאילו, אתה אומר, בפועל מה שמפחיד ביניהם זה הבחירה של הסאבספייס, וקודם זה לא היה משנה איזה סאבספייס אני בוחרת.
נכון, את אותו טיעון אפשר לעשות גם רק כשעשינו output unit אחד. עדיין שגם כל עוד ה-input noise לא הולך לאפס, ממש, אז אני ארצה לעשות projection ל-first principal component. זה נכון שאת יכולה להגיד, אולי באיזשהו שלב, אם האינפוט זה כל כך חלש שזה לא משנה, אז זה לא משנה, אז אין סיבה שם. אבל למשל, המערכת הראייה היא צריכה להתמודד עם טווח מאוד גדול של ערכי אלוקים. אז יש, גם בזה שהיא בוחרת משהו שיהיה טוב לסאבספייס, היא בוחרת בצורה, תמיד בצורה שתהיה.
montre maintenant, si tu veux. Enfin, non, peut-être exactement. Ouais, et ça, ouais, et d'ailleurs, c'est évident quand tu me l'as dit, c'est-à-dire que quand tu conditionnes sur. Ouais, toute chose n'est pas égale par. Ouais, ça, non. Comme là, j'ai N-1, c'est pas vrai. Non, ok, j'aurais une égalité. Ça, je fais stationnaire, c'est une égalité. L'égalité, elle vient du fait que. Là, j'ai pas encore parlé du stationnaire. Là, en fait, je fais d'abord. En fait, là, je dis que j'ai une suite décroissante qui est minorée. Et là, je montre qu'elle est décroissante, donc ça, je montre un peu rapidement. Elle est minorée, donc elle a une limite. Donc elle est limite finie, donc elle est stationnaire. Et puisqu'elle est stationnaire, ça veut dire ça. Si elle est stationnaire, forcément, ça veut dire que toutes les valeurs sont égales, que quand n tend vers l'infini, dans la limite où n tend vers l'infini, toutes les valeurs, tous les hn deviennent égaux. Ils sont d'accord. Oui, ça, mais c'est la limite quand n tend vers l'infini. Ouais, de 1 à n-1, j'ai mis les deux, mais c'est 1 à n-1. Parce que toi, tu l'avais présenté différemment, donc je sais plus comment dire. Tu avais d'abord dit qu'elle est stationnaire.
לא תלומה, זה יחסי.
לא שבשלילי.
לא, לא, לא. זה זה יחסי. כאילו בכלל, אם זה יותר גדול או קטן מאחת, זה לא, אין לזה כל כך... אם כבר, אז כאילו צריך לשאול לא אם זה שלילי, אלא אם זה יותר קטן מאחת, אבל זה לא כך, זה לא הנקודה, זה שאלה יחסית, באופן יחסי. אוקיי. Alright, so after discussing at length what we think should happen, we delve now into the math, and that's more technically more complicated, but it's still very beautiful, because first of all, when you have the full mathematical treatment, you can predict what should be these alphas and what should be the representation for any situation, and also we will see that the theory actually will tell us that in these two limits that the result is exactly what we wrote. One comment about notation, you see this q minus delta, I'm going to denote it by large Q. And it has a clear interpretation. The small q is the amount of variance that you want to have in each output unit. Part of it comes from the output noise, right? That's the delta. So q minus delta is the amount of variance that remains for the for this part, the part that comes from the input with the input noise, and then so it's just convenient to use this notation. I'll do it in a moment.
Is it the variance of the input and the input noise together?
Yeah, small q is the variance of everything in each output unit, or per output unit. It's on average. And then q minus delta is the average amount per output unit just for the part that does not include the output noise. Okay. Okay, so now let's start the full mathematical treatment. Well, should I do it? Yeah, I will not do it here. I think that I will erase everything from here on. No. I will erase everything from here on, and then we'll do it because it's nice to have. It's nice to have this written down. You know what? I will just start here. Full mathematical treatment. Okay. So, what we need to write down is this mutual information and the constraint. Okay, so actually I will not go through all the details. I will write the expressions, and it will be your work goal in an exercise to derive everything in detail. So one thing that we will need is the covariance matrix of the outputs, which I think we already wrote. And I think that even then I did not derive everything in detail. So this ends up having three components. There's a component, bless you, there's a component coming from X, the real input. And then there's a component coming from the input noise, which still goes through W. So this involves the variance of the input noise and the structure of W. And then there's a component coming from the output noise, which is simply proportional to the unit matrix. So that's the variance. This is the covariance matrix of the outputs for any choice of W. And what we need to optimize is the mutual information. So let me write down the mutual information. And again, I'm not deriving everything. So this involves the expressions for, but actually, this involves the expressions for mutual information of Gaussian variables. We have the entropy of the outputs. So you should actually know that this can be written as epsilon, the determinant of this matrix for a Gaussian variable. And then we need to subtract the entropy of the outputs conditioned on the inputs, right? So how would that be different from this expression? It's just without the signal part, right? So this will be minus half ln determinant of epsilon W transpose W plus delta I. And that's a mutual information, but we have a constraint. We have this constraint, so we will add that into this Lagrangian, into this function that we're optimizing as with a Lagrange multiplier. So I will add a term which is half lambda. Now, often we use lambda for Lagrange multipliers, but lambda is already taken by the eigenvalues of the matrix. I don't want to use small lambda, so that's why I'm using large lambda. But this is a Lagrange multiplier. And now I need to simply write down the constraint on the constraint. So I need to write down the variance, the sum of the variances of the output unit. How can I write it using this expression? It's a trace, right? Because it's just the sum, the variances of the output units are just the variances of the individual elements, which are the diagonal elements of this matrix. So I will have here trace of W transpose CW plus epsilon trace of W transpose W minus M times Q minus delta. Okay, so there's plus M times delta, which is the trace of this, and then there is minus M times Q, which is coming from the constraint. And this is what we called Q. Okay, so this is what we need to optimize. Now, before we go ahead and actually optimize it, I want to note something interesting about this Lagrangian. And so the interesting thing is that L is invariant to any unitary transformation. I will explain in a moment. Of the output. So imagine that we have a set of weights, W transpose. Okay, so in general, we view this Lagrangian now as a function of the weights, right? That's what when we're optimizing the weights. And I claim that if you take a set of weights and you replace them by another set of weights, which is related to the first one by a unitary transformation, what does unitary transformation mean? It means that U transpose is the unit matrix. Sorry, U transpose U is the unit matrix. Also U transpose. So unitary transformations are very special transformations that linear transformations that preserve length. That any vector after the L2 norm of the vector before the transformation and after the transformation remains the same. And basically what they are rotations and reflections. Okay. So these are rotations. These are basically rotations. It's like a transformation that maintains the length and also the angle between any two vectors. So I claim that if you take a set of weights and you multiply them by a Unitary transformation, which you can think of it as two steps: generating a set of outputs and then rotating them, generating another set of outputs which is related to the first by a rotation in the m-dimensional space, I claim that L does not change. This you should check. Okay? But for example, W transpose W, just as one example, W transpose W will go into W transpose. It will go into the trace of a UW transpose W U transpose, and in the trace you can show that it's the same. So every one of the elements in this expression do not change if we do this manipulation on W. That tells us something very important. It tells us that there is no unique choice of the weights. Any choice of weights that you will give me that is optimal, there are many, many other ones which correspond to this rotation. And this goes back, that's what you asked me earlier, which is, in what sense, when I talked about instead of encoding the principal components, encoding some linear combinations of them. So we will see in a moment, I will tell you in a moment, that doing this, extracting the first principal components and having each one of the output units representing the coefficient of one principal component is a good way to do things. But we may just as well take the outputs that we would get in this way and combine them in the rotation in n-dimensional space, and that will work just as well. That's mathematically, we see this from here. It will not change the Lagrangian, any element in the Lagrangian. Okay? So this is one thing that I wanted to note. And now, okay, so this will be an exercise. Actually, several things here in what I derived. And now I will tell you a theorem. And maybe I will move this to here.
Is there any reason you multiply the Lagrangian by -x?
It's just for convenience, because we will get later on some expressions that involve this large lambda, and it will just look a bit nicer. So it doesn't matter at all. We could have not put variable have. Okay, so I will not prove this. The theorem, one optimal solution for W has the following form. This is U transpose 1. This is U transpose 2. This is U transpose M. So what I've wrote so far, this is N, this is M. So what I wrote so far is the matrix that you would apply to the inputs in order to extract the coefficients of the first M principal components. And then here I will multiply this by another matrix that has square root alpha 1, square root of alpha 2, square root of alpha M. So this is exactly the matrix that I wrote here, right? And so again, this means extracting the coefficients of the first M principal components and multiplying each by some factor. And we still need to, so it has this form. We still need to specify what are alpha 1 up to alpha M. we'll need to work in order to do that. And so I will denote this form of the matrix by the principal components, the PC solution, principal component solution, because in this form, as we discussed, we're encoding each one of the coefficients independently of the others. And just to clarify some notation, we assume that lambda 1 is larger than lambda 2, which is larger than lambda 3, and so on. And the alpha i's that appear here depend on the parameters in a way that we still need to specify. What are the parameters? The parameters are all the lambdas, 1 to m, or lambda 1 up to lambda m. They are the input noise and the output noise, epsilon and delta, and q. Am I forgetting anything? No. So these are all the parameters that can affect what are the best choice, what are the optimal choices of the alpha. And so that's one thing. And second,
What do you mean?
that's one statement.
No, but the PC solution?
This is how I call this solution.
Okay.
Okay, this is just a name. And all and the second claim is that all other optimal solutions are of the form W transpose equals U W transpose PC, where U transpose U is equal to the unity matrix. Okay. So there are many possible solutions, but all of them are rotations of one solution. And one way to do it is to encode each one of the coefficients of the principal components independently of the others. But in fact, we can also combine them with rotation. Okay. So now we need to find what are the alphas. So
Isn't the Lagrange alpha? Is that
isn't what large lambda?
the Lagrange?
Not really, because the Lagrangian needs to be tuned in order to obtain the constraint. So I could have written here instead of Q, I could have written the Lagrange multiplier. There's a one-to-one correspondence between a choice of this large lambda and Q. Okay, so let's continue here. So now I want to discuss the WPC solution. So the idea is now to plug in this form of the matrix into this expression. Okay? And what happens is that for this particular choice of the matrix, because these vectors are eigenvectors of C, what happens is that we just get here relatively simple things. So, for example, when we take W transpose PC and multiply it by the covariance matrix, which appears here, and multiply again by WPC, what we end up with is a diagonal matrix. So the jth element of this is alpha j, lambda j, delta jk. This is an exercise. I will not do it. Okay? But it's in a diagonal matrix, and we know what's in each diagonal element. And when we take WPC transpose and multiply by WPC, which is also something that we need to do there, it's also a diagonal matrix, and the elements are simply alpha j, delta jk. Okay? And so for diagonal matrices, things like this are very simple, because the determinant is then just the product of the elements on the diagonal, and the log of the determinant is just sum of the logs of the elements of the determinant. So L, what will we have for L? We'll have half sum over j going from 1 to m, the log of the elements in the diagonal, which are alpha j, lambda j, plus lambda plus epsilon alpha j, right? This is these elements, and then there are these elements, and then there's plus delta, minus half ln, same thing without this part. So it's epsilon alpha j plus delta. And then here the trace is also simple. A trace of a diagonal matrix is just the sum of the elements. Well, it's always the sum of the elements of the diagonal, actually. So we have here large lambda over 2, sum over j, alpha j, lambda j, plus epsilon sum over j, alpha j, minus m q. So you see that by choosing this set of projections, the problem becomes much nicer, because instead of having a determinant of an of a m by m matrix, we just have a sum over m terms, because there are only elements in the diagonal. And so now what do we need to do? Now our parameters, instead of being all the elements of W, we just have, these are our parameters, alpha 1, alpha 2, up to alpha m. We want to find the best ones. So we just take a derivative with respect to alpha and require that that's 0. So we need to take a derivative with respect to alpha I and require that that's 0. And that's not a lot of work, but I will skip the algebra. And the equation that we get out of that is the following. So I will simply write it down. So you see that the nice thing is that for the PC solution, once we plug it in, we actually get a separate equation for each one of the alphas, which relates it simply only to its own lambda. Each one of the alphas, because the structure of the structure here, which is just a sum over terms, which involves the alpha j's and the alpha j's, each one of the alpha j's is related only to its or alpha i's here, related only to its own lambda I, almost. There is some coupling between all the alphas. Where is it coming from? So see, using this equation, I would be able now to express alpha I as a function of all the other parameters that exist here. And I claim that it's almost as if each alpha I depends only on its own lambda, but it actually in a subtle way depends also on all the other ones. Can you tell me how?
Capital lambda through Q.
Exactly. So we have this capital lambda, so if I tell you what is capital lambda, each alpha I depends only on its own lambda. But this is not what we really care about. What we really care about is the constraint. And so we need to tune for any choice of this lambda. So this equation gives us, let me write it down explicitly, and then I explain again. This equation gives us alpha I as a function of lambda I. This is an implicit equation that has a solution, one solution. So alpha I is a function of lambda I, epsilon, delta, and large lambda. Right? But we have a constraint. Our constraint is that sum over alpha I, that the trace, this is actually the expression that appears here. And that ends up being that the sum over alpha I, lambda I plus epsilon is equal to mq. I'm using the large Q. So there is some complicated function which is just a solution of this equation again that relates alpha I to lambda I and all these, and epsilon, delta, and lambda. Epsilon and delta are just given. But this large lambda, for any choice of it, this will determine all the alpha I's in a monotonic way. Okay, we'll discuss this in a moment. And now we need to tune this large lambda until we obey this constraint, and that will determine all the alpha I's. Okay.
Wait, I still don't see how
So
how this relates the alpha to all other lambdas.
because because the correct choice of large lambda involves all the small lambda, all the small lambdas, right? And so it's through this that all the alpha I's depend actually on all the lambdas and not just on their own. Okay. So let's see how we're doing on time. Yeah, we have some time. So what I want to do next is revisit our discussion on what happens in the limit of low input noise and the limit of high input noise. Let's see if these equations, so this is, in a sense, determines the structure of the solution completely. There's some subtle issues to discuss about it. We'll do it a bit later. But I now want to see that these equations actually recover what we argued should happen in the limits of low input noise and large input noise. So I will start here. Low input noise. So now, once we have these expressions, we can start to see what low means. So input noise is epsilon, right? And I want epsilon to be small. And in order to really assume that it's small in every element in this expression, we now see what it needs to be small compared to. What we will assume is that epsilon is small compared to all the small lambdas, which means that the noise in each direction, in each one of the m directions, the noise is small compared to the variance of the inputs. Okay, so that's one thing that we assume. The other thing you see here that epsilon alpha i's, we will want to neglect it compared to this term. Okay, so epsilon is small compared to lambda, that's one thing, but we will also want to neglect this term compared to this one. This has a different interpretation. This has the interpretation that the input noise, once it's multiplied, goes through the weights. The contribution of the input noise in each one of the output units will be small, will end up being small compared to the output noise. Okay? So this has to be verified if that's true or not. Depends also on the weights. But we're going to assume that we're in a regime where the noise is sufficiently small, the input noise is sufficiently small, such that after going through the weights, it will also be small compared to the output noise. So, in other words, what we're going to assume is that epsilon is small compared to all lambda I for I going from 1 to m, and epsilon alpha I is small compared to delta for I going from 1 to m. Once that is true, this equation becomes quite simple. What it tells us is that lambda I divided by lambda I alpha I plus delta is equal to, second term we can neglect, so it's equal to large lambda lambda I which means that alpha I lambda I plus delta has to be equal to 1 over large lambda. And in fact, in order to obey the constraint, this has to end up being equal to Q. And so we get exactly, what we get here is exactly the result that we wrote previously. We get that alpha I is equal to Q minus delta, which is what we call the Q, divided by lambda I. And so large lambda, small alpha. This is exactly what I wrote. So we see that we get this from the equations. Sometimes this kind of transformation where you equalize the variance of all the inputs is called whitening. For those of you who know what white noise is, you can understand maybe why this is called this way. We equalize the variance in all the directions. Okay. Now let's see what happens in the limit of large output noise. Large input noise, sorry. So what we're simply going to assume is that epsilon is much larger than lambda I for all I, or I going from 1 to m. And so to understand what happens in these equations in this limit, the way we're going to think about it is as follows. We have here two expressions which are the same, except that what the role played here by epsilon is played here by lambda I plus epsilon. Okay? So so let me write it. I'll take this equation. First of all, in this term, I will neglect lambda I compared to epsilon. So I write that large lambda times epsilon is equal to lambda I plus epsilon divided by lambda I plus epsilon alpha I plus delta minus epsilon divided by epsilon alpha I plus delta. Now the thing is, I want to, as I mentioned, I want to neglect this compared to this. But if I simply neglect it, I get that this is equal to this, so I just get 0, which is not interesting. So we need to get a correction. We need to get an expression for the difference between these two quantities. And so I will think about this as some function of the variable x, which is lambda I plus epsilon. And so what we have here written is f of x, or f of x equals lambda I plus epsilon minus f of x equals simply epsilon. And we will approximate this by the Taylor expansion of this function f around epsilon. Because lambda I is small compared to epsilon. So f of lambda I plus epsilon minus f of epsilon is approximately given by f prime of where x is equal to epsilon times lambda I. Right? And so if you do this, I will not do it explicitly. What we get is that large lambda times epsilon is given approximately by delta times lambda I divided by epsilon alpha I plus delta squared. This is just an approximation to the difference between these two terms. Okay? And therefore now what we want is alpha I. So I will just invert it to get alpha I. So this is telling us that alpha I, or epsilon alpha I, is equal to the square root of delta lambda I divided by lambda epsilon minus delta. So what is interesting in this expression is to see how it depends on lambda. What you see in this expression is that now in the limit of large input noise, large lambda gives us large alpha. This is the opposite of what we got in this case, right? So indeed, the theory predicts that when the input noise is large, we will actually devote more resources to the components with large input variance versus the components with small input variance, opposite of what we do in the limit of low input noise. And the theory tells us exactly how alpha should depend on lambda. I will continue for a few more minutes. I just want to write down